Okay, so last time we started the representation theory of SU2. So let me start from the very beginning so that the recorded version is self-sufficient. So what we want to develop is the finite dimensional unitary representations of the Lie algebra or the Lie group of SU2. Okay. So if we develop the Lie algebra, we can exponentiate that to get the Lie group for free. Okay, so let's start. So before we start that, let me just emphasize the importance of this subject. Okay, let's see if I have any message. Okay, let me just emphasize the importance of this subject. The construction of the irreducible reps of SU2 form the backbone of representation theory. Okay. So next week, we will do the representation of SU3, and that'll be the last topic that we cover. And you will see that the construction that we have about SU2 will actually form a very important part of that. Okay, so let's start with the Lie algebra of SU2. Okay, somebody's hungry, so can you give me 1 minute? Let me just feed her. Okay, so I'm back. So let's start with the Lie algebra of SU2. Okay. Can someone remind me what it is?
Is it like tau 1, tau 2 commutator equals I epsilon ijk tau k?
Yeah, so if you say tau 1, tau 2, on the right-hand side, it should be epsilon.
Oh yeah,
1,
I mixed those up. Yeah, sorry.
Okay, so it's traditional to use J because of the angular momentum connotation. So JA, JB is equal to I epsilon ABC JC, where there is a sum over C, but since these indices take only 3 values, there is no sum, right? Because if this is 1, this is 2, this has to be 3. Because all the other, the structure constants are 0 when 2 of the indices are the same, right? And in this case, the structure constant for SU2, we have chosen the structure constants to be, it's possible to choose it to be epsilon ABC. Okay, so there are 3 non-trivial equations here, right? We can take the value of the index to be 1, then we have J1. Then the second one has to be J2. Of course, if I take both A and B to be the same, then the commutator vanishes, right? By definition, because the commutator is an antisymmetric object. So J1, J2 is I So if epsilon is 1, epsilon is 1, 2, then the third one must be 3. But we know that epsilon 1, 2, 3 is by definition 1, so we get J3. So this is the first relationship that we get from this commutation relationship. The second relationship is when we have one of the indices J2, the other index is J3. Then we have I epsilon 2, 3, and then the last index must be 1. So we get J1. So then this is I. Again, this is an even permutation of this thing, right? Because it's an even permutation, we get, again, +1. Okay. So the number 3 is when one of the indices is 3, and the other one is 1. Then we have I epsilon 3, 1, 2, J2 again. This is an even permutation of this thing. Then we have I, J2. So these are the 3 non-trivial commutation relationship that we have from, that which are the components of this equation. Okay, we are dealing with unitary representation, and we know that the SU2 is a unitary group, and therefore the generators must be what? If SU2 is unitary, then what conditions do the J's have to satisfy?
Permission.
Right. So all these J's are Hermitian. Okay. So to develop the representation theory of the SU2 algebra, we have to follow Cartan and do something very clever. We introduce a different basis for the Lie algebra, a non-Hermitian basis. Okay, so we introduce a different complex basis for the Lie algebra of SU2. And we define J plus to be J1 plus I times J2. And we define J minus to be J1 minus I of J2. And we keep J3 as it is. So now our new basis consists of J plus, J minus, and J3. And J3 is still Hermitian. But J plus, if I take the Hermitian conjugate, let's see what happens. We have J1 plus I of J2. If I take the Hermitian conjugate, J1 is Hermitian, so this is just J1. I becomes minus I because it's a number, so Hermitian conjugation is just complex conjugation, and J2 is also Hermitian. So we see that when we take the Hermitian conjugate of J plus, I get J minus. Similarly, the Hermitian conjugate of J minus gives us J plus. Okay. So now you should be able to show very easily that in this basis, the commutation relationships, the 3 non-trivial commutation relationships, become J3 commutator of J plus minus is equal to plus minus of J plus minus. These are 2 commutation relationships. And the other one is the commutator of J plus and J minus is 2 times J3. Okay. So you should be able to show this very easily.